Hello students. This lesson is the second part on analyzing functions. We will cover power functions briefly, exponential functions in more depth, and logarithmic functions. Graph a few examples of each kind of function below. Give the domain, range, intercepts, and end behaviors. Now this first class of function is called power function. It has the form y equals x to the p. And let's limit our domain to positive values of x only, but we can use any exponent p, and p stands for power. We'll use technology to explore this. So I've typed in f of x equals x raised to the p, and then curly brackets x bigger than 0. Then we are prompted to add a slider for p. When p is 1, we have the graph of y equals x, which is a line, slope 1. Two key points on this are 1, 1 and 2, 2. If you do a trace, you'll see that we have an undefined point at the origin. That is because I'm defining this function only for positive x's. If we increase p to 2, we get the right side of y equals x squared. Change p to 3, and we have the point 1, 1, and also up here the point 2, 8. This is the right half of a cubic function. P back to 1, and now I'm going to play p and let it increase and observe the behavior of the graph. As p increases, we get steeper and steeper curves going upwards into the first quadrant. As p decreases from 1, we get graphs that arch over to the right, and by the time p gets to 0, it becomes a horizontal line, because x to the 0 would be 1. When p is 1/2, x to the 1/2 is the square root of x, and so we're seeing the top half of a sideways parabola containing the key point 4, 2. If I type in p equals 1/3, we have x to the 1/3, which is the cube root of x, containing the key point 8, 2. As p decreases from 0 into negative values, we get functions that follow the x and y axes as asymptotes, subtly changing shape as p decreases. When p is -1, and this is a very common function called the reciprocal function 1 over x. When p is -2, this is the function x to the -2, which is 1 over x squared. Now I'm going to let p vary from -3 up to +5. As p gets closer to 0, it becomes a horizontal line. When p is 1, it's a straight diagonal line with slope 1. And as p continues to increase past 1, we get very steep increasing functions. Notice in all cases we go through the point 1, 1, because 1 raised to any power will give you 1 back. Now these functions are defined for x being positive, and when p is 1, we get this ray starting with a hollow point at the origin. When p is more than 1, we get a very steeply increasing non-linear curve. When p was between 0 and 1, we get an increasing curve, but it's flattening out as we head to the right. When p was 0, we had a horizontal line off to the right at height 1. And when p was negative, we had a curve in the first quadrant that followed the axes as asymptotes. And all of them go through the point 1, 1. Now I'll make a table where my headers will be the value of p, the domain, the range, and then what are the y-coordinates doing as the x-coordinates get large, and what are the y-coordinates doing as the x-coordinates approach 0, and that little plus sign means from the right. We can't let x go to -infinity because we've defined this function only for x being more than 0, but we can analyze what will happen to the y-coordinates as x gets closer to 0. So if p was positive, we have the domain is 0 to infinity, and in these three cases, as we go to the right, the y-coordinates will increase to infinity. So the range will be 0 to infinity. The y-coordinates will approach infinity as x approaches infinity. And these three colors, as x gets closer to 0, all of these graphs approach the origin. If p is 0, that is the blue one, same domain. The range, though, becomes a single possible output of 1. As we go off to the right forever in this graph, the y-coordinates approach 1. And as we get closer to the y-axis, the y-coordinates are also getting closer to 1. And if p is negative, the orange graphs, we have the same domain, a range again of 0 to infinity. But as we go to the right forever with the orange graph, the y-coordinates approach 0. And as we approach the y-axis, which is to say as x gets closer to 0 from the right, the y-coordinates go up forever to infinity, following an asymptote. Now let's look at exponential functions. Exponential functions have the form y equals b to the x, where b is called the base. It must be positive, but it can't be 1. Notice a key distinction between power functions and exponential functions is where the input variable is. In the case of exponential, we have a constant raised to the x, where x is the variable. And in the case of a power function, we have x raised to a constant. Type in f of x equals b raised to the x. This time no domain restriction. Add a slider for b. We do want the base to be positive, so let's let the base vary from 0 to 10. You can see when the base is 1 that we just have a horizontal line, so this is of little interest, which is one reason why we exclude the base being 1. If the base is 2, we have an increasing function. 3 key points going left to right. When x is -1, we have 2 to the -1, which is 1/2. When x is 0, 2 to the 0 is 1, giving us 0, 1. and when x is 1, we get an output of 2. And this is known as a growing or increasing exponential function. If we increase the base to 3, notice these key points. The one on the left is negative 1, comma 1/3. We're seeing a decimal version of that. 0, 1, and then 1, 3. And we have an even faster growing exponential curve. Increase the base to 4. The 3 points are negative 1, 1/4, 0, 1, and 1, 4. One important base is the base e, Euler's constant, about 2.718. The 3 points you're seeing here are negative 1, comma 1 over e, 0, 1, and 1, comma e. But now let's explore what happens if we go less than 1. If the base is 1/2, notice these key points. On the left, we have negative 1, 2. That's because 1/2 raised to the minus 1 gives us 2 raised to the positive 1, which is 2. 1/2 raised to the 0 gives us 1. And then 1/2 raised to the 1 is 1/2. Animate the base as it decreases from 1 towards 0. When the base is 0, we have an uninteresting function, so we don't let the base be 0. But if you park the base anywhere between 0 and 1, we have a decreasing or a decaying exponential function approaching the x-axis as we go to the right. Now I'll let the base vary from 0 to 5. We begin with decaying exponentials, a flat line, and then increasing exponentials. Now in the graph, I have plotted simultaneously b to the x and 1 over b to the x. So when b is 2, the red graph is 2 to the x, and the black graph is 1/2 to the x. Now if I play b from 0 to 5, you will always notice that these graphs are symmetric with respect to each other across the y-axis. And regardless of the base, as the base varies, we have 2 key points, 0, 1, and 1, comma the base. The domain is all real numbers, and the range is positive outputs only. So in summary, when the base is more than 1, we have a growing exponential. And when the base is somewhere between 0 and 1, we will have a decaying or decreasing exponential. In both cases, 1, comma b will be a point on this graph, and negative 1, comma 1 over b will also be a point on this graph. And they all share the same y-intercept at 0, 1. When the base is more than 1, the domain is all real numbers, and the range is positive outputs only. And as we go to the right on a growing exponential function, the y-coordinates go to infinity. But as we go to the left, the y-coordinates decrease to 0. And when the base is between 0 and 1, we still have a domain of all real numbers, a range of positive outputs only. But this time, as we go to the right forever, the y-coordinates are approaching 0. And as we go left, the y-coordinates go up to infinity. All right, let's go to the next page. Graph the functions below, identify any asymptotes, and determine the end behaviors. Here, these are transformations of some parent graphs. The parent graph here is 2 to the x. It'll pass through 0, 1, 1, 2, and negative 1, comma 1/2. And I'll only keep track of these 2 points as I do transformations. It is a growing exponential. When I multiply this function by a negative, we will reflect across the x-axis. So 0, negative 1, and 1, negative 2 will be points, and we'll have this green graph. When I replace x with x plus 1, we shift left 1 unit. So both of these green points, move them left 1 unit, and imagine the whole graph moving left 1 unit. And then finally, the plus 4 at the end is a shift up 4 units. So move the 2 blue points up 4 units. And another key feature that will shift with the graph is the graph's asymptote. So the vertical shift moves that asymptote to the line y equals 4. So in the end, we have a graph going through the points negative 1, 3, 0, 2, and then you can find others if you'd like. We have an asymptote at y equals 4. And as x approaches infinity, the y-coordinates of the black graph will go down to negative infinity. And as x approaches negative infinity, meaning we go left with the black graph forever, the y-coordinates are getting closer and closer to the height 4. Okay, now let's look at g of x. The parent function here is e to the x, which passes through 0, 1, and 1e. E is about 2.7, and we have a growing exponential function. Now the first transformation is to change x to negative x, which is a reflection about the y-axis. So the point 0, 1 will not move. 1e will become negative 1e, and we will now have a decaying exponential. Recall that another way to think of e to the negative x is to write it as 1 over e raised to the x, and this base now is between 0 and 1, hence the reason we have a decaying exponential. The next transformation to consider is the 1/2 times e to the negative x. This is a vertical stretch by a factor of 1/2. That means this point here will now be 1/2 as far from the x-axis than it currently is, putting us roughly at this location. The y-intercept will be 1/2 as far from the x-axis as it currently is, putting us here. And we still have a decaying exponential. This first blue point is at negative 1, comma e halves, and the other blue point is at 0, 1/2. And now the final transformation is to subtract 2 from the rule, which is a shift down 2 units. So take this blue graph and shift it down 1, 2 units, keeping track of the y-intercept and the new horizontal asymptote. And this new horizontal asymptote is y equals negative 2. Our y-intercept is 0, negative 1.5 or negative 3 halves. And our other black point is at negative 1, and then we had e halves and then subtract 2 from that. Now the second black point is very easy to verify. Just look at the rule of the function and plug in negative 1 for x. And you'll get e to the positive 1, or just e, and then times 1/2, and then minus 2. Exactly what this y coordinate is here. Now, as x approaches infinity, as we go to the right forever, the y coordinates will get closer to this asymptote of negative 2. And as x approaches negative infinity, so as we go left forever, the y coordinates of the black graph will go up to positive infinity. Okay, moving on to the next page. Find the exponential function shown below by finding the values of a, b, and c for each form below. Let's focus on this first form here, and then we'll talk about how to find the second form. The plus c accounts for a vertical shift. The a is a vertical stretch and or reflection, depending on if a is negative. And then we have an unknown base of the exponential that needs to be found. Well, a and c will be easy to find. First, identify where the horizontal asymptote is. You can clearly see it here at y equals negative 3. This tells me that the c value must be negative 3. A vertical shift is the only way to move the horizontal asymptote away from the x-axis. Now, ordinarily, an exponential function that has not been vertically stretched passes through a point that's only 1 unit away from the asymptote. But in this case, our y-intercept at 0, negative 1 is 2 units away from the asymptote, suggesting that we had a vertical stretch by a factor of 2. This is the only way to move the y-intercept closer to or further away than 1 from the horizontal asymptote. And that is because this structure is not allowing us to do any horizontal shifting, which is another way that we could widen or lessen that gap. But given that we only have vertical stretch and vertical shift in these forms, then the vertical stretch must account for that gap. Now this is clearly a decaying exponential, so I do expect this base in the end to be between 0 and 1. Now to find the base, we do need to find another point somewhere on this curve, and try to find one that involves only integer values. And the one that grabs my attention is right here at negative 1, 3. Well, these are x and y values. So I'm going to rewrite form 1 with the information we do know. We know a must be 2. We don't know b. And we know that c must be minus 3. Now for x and y, I can plug in the values negative 1 and 3, and then I'll be able to solve the equation for the base b. So we get 3 is equal to 2 times b to the minus 1, and then minus 3. We add 3 to the other side. Now divide both sides by 2. Keep in mind that b to the minus 1 means 1 over b, and now I can invert both sides. So b must be 1/3, exactly as predicted. So y1 is equal to 2 times, and then I'll put the base in parentheses, that's being raised to the x, and then minus 3. Now to achieve this second form, the only difference is that we want a negative in front of our x. This will mean that we don't have necessarily the same b value as we do in the first case. However, the a and the c must be the same. In fact, if I begin with my first form, then the easiest way to achieve a minus sign in that exponent is to rewrite 1/3 as 3 to the minus 1. And then when you have 3 to a power and then raised to another power, you multiply the powers. So we get y equals 2 times 3 to the negative x minus 3. And this gives us our second form. These functions produce the same graph. And that is because 3 to the negative x can be rewritten as 1 over 3 to the positive x, because this is the rule of negative exponents. Keep in mind that if you graph 3 to the x, you get a growing exponential. And if you invert the base to 1/3, or if you replace the x with the negative x, both ways of thinking should produce a graph that is a mirror image across the y-axis. Notice that as we go right forever with this graph, the y-coordinates are approaching that horizontal asymptote of negative 3. And as we go left forever with this graph, the y-coordinates are approaching infinity. We could have determined this right away from using the image alone. All right, moving on to the next page. Here we begin talking about logarithms. Now this is a review from algebra classes, and this should not be the first time you are seeing logarithms. A logarithm represents an exponent needed on a certain base to achieve a certain result. Consider the equivalent statements below. Here we have b raised to the c is equal to a. This is known as exponential form. This can be rewritten as c equals log base b of a. And this is known as logarithmic form. For example, we know that 2 cubed is 8. In log form, we would say that log base 2 of 8 is 3. This logarithm represents the exponent needed on 2 to produce 8, and that exponent is 3. The b is called the base, the c is called the exponent, And in this context, a is the output or the result of the exponential. In logarithmic form, we still call this b the base. We call the a the argument of the log, and c we'll call the output of the log. Now this c is an exponent because in the exponential form, it has the role of being the exponent on the base b. Now in both forms, b must be positive but not 1. The c can be any real number, but the a must be positive. Now simplify each logarithm by hand as much as possible. Use technology for the rest. So log base 7 of 1. This represents the exponent needed on the base 7 to produce 1. So you can put a question mark here for now, and then ask yourself, 7 raised to what power will equal 1? And of course, the answer to this is 0, so this logarithm is just 0. Log base 3 of 9. 3 to what power equals 9? Well, the answer here is 3 squared, therefore this logarithm is just 2. The next one, 4 raised to what power will equal 4? Well, here the answer is 4 raised to the first power, so this logarithm is just 1. Now this next one, 5 raised to what power will equal 0.2. It's helpful to write 0.2 as 1/5, and now we can see that the power needed is a negative 1 power. So this logarithm will simplify to negative 1. The next one's a little bit tricky. 25 raised to what power will also be 1/5. Well, we need to square root the 25 to make it a 5, but then also do the reciprocal of 25. A 1/2 power will do the radical, and a negative 1/2 power will also do the reciprocal of the base. Right, recall that 25 to a negative power means to do 1 over 25 to the positive version of that power, which means do radical 25, which gives us the desired 1/5. So this logarithm is negative 1/2. The next one is 3 raised to what power will equal the square root of 3. Well, here we just have to interpret a radical as a power, and that power is 1/2. So this logarithm will simplify to 1/2. The next one, 2 raised to what power, will give you 0. Well, the range of an exponential is positive numbers only. It's impossible to do an exponential and get 0 back. Remember, the result of an exponential is a, and a must be positive. So you cannot get a negative or a 0 result of an exponential. So in the context of a logarithm, it means that the argument of a logarithm must also be positive. It cannot be 0, cannot be negative. So we'll say this is impossible, and this logarithm does not exist. In the next case, 2 raised to what power will equal negative 3. This one is also impossible for the same reasons. The argument of a log cannot be negative, cannot be 0. So again, a D and E. Now this last one, 2 raised to what power equals 3. Well, this one is possible, but it's not a convenient number. So we reach for the calculator, type in log, hit this subscript button, base 2, and then I like to put the argument in parentheses, and the argument here is 3. And we get about 1.585, rounding to 3 decimals. So what this is telling us is that approximately 1.585 is the exponent needed on 2 to produce 3. So logarithms give us the means to solve these kinds of exponential statements for missing exponents, where the answers are not convenient numbers. And in reality, this would be an irrational number with decimals that go forever without a repeating pattern. So using technology, we can find that value. Now there are 2 logarithms with bases that use special notation. The common log, if you see a log of a and there's no base written, then there's a default assumption. We assume that this is a log whose base is 10. So in this first example, log of 1,000 means that we are looking for an exponent needed on 10 to produce 1,000. And of course that exponent would need to be 3. So this logarithm is just 3. The next one, we're looking for an exponent needed on the base 10 to get 0.1. Rewrite 0.1 as a fraction, 1/10, and then hopefully it becomes obvious that the power needed here is -1. So this logarithm is -1. Now log of 3, this means we're looking for a power needed on 10 to produce 3. This will not be a convenient number. So we type in log, and you don't need to write the base. I'll put the argument in parentheses, and we get this number, which is the same result I would get if I had put the base in there of 10. So about 0.477. Okay, next we have the natural log. The natural log is represented by an ln, and when you see ln of a, this means we're doing a logarithm whose base is Euler's constant e. So in this first case, you see natural log of e. I imagine that there is a e base as well, and then I ask myself, e raised to what power will equal the argument e? When you see it this way, it should be obvious that that power we need is a 1 power, so this logarithm simplifies to just 1. In the next case, e raised to what power will equal 1? And the power needed on any legitimate base to produce 1 is always a power of 0. So this logarithm just becomes 0. And in this third case, we're doing e raised to what power will equal 3. Well, this will be a scenario, again, for which we need a calculator. So you can type in ln of 3, and we get this number. Or you can type in log base e of 3, and you see you get the same result, about 1.099. I encourage you to type in many of these logs using a calculator to confirm the answers we've been getting, even for those cases where we did not need a calculator. and see what the technology says in those cases where we said the answer was does not exist. Okay, moving on to the next page. Know the following 9 properties of logarithms. Now the properties are all summarized in this first column, where the base b is kept general, and the next 2 columns are just repetitions, but in the specific case where the base is 10. So every time you see a little b as a subscript on a logarithm, you see over here no subscript written, which means that we're talking about base 10. And over here we're talking about natural logs. So take all these log base b's and just write them as ln's, which are logs base e. The sooner you learn these, if you don't know them already, the better. Now, property 1 is just a restatement of log form being equivalent with its exponential form. Property 2 says that the log base b of 1 will always be 0 because b to the 0 is 1. Property 3 says log base b of b is 1 because b raised to the 1 power will give you b back. Property 4 is log base b of b to the a will always simplify to a because b raised to what power equals b to the a, and the answer to this question stares us in the face, and the answer is a. You can think of logs and exponentials of the same base as being inverses of each other, meaning that a cancellation occurs and you get a back. Property 5 is related to this idea of canceling of inverse functions, and b raised to the log base b cancel each other as well, and you just get a back. So for example, 2 raised to the log base 2 of 8 will give you 8, and that is because log base 2 of 8 represents the exponent needed on 2 to produce 8, so what I just shaded would be a 3, and then if I do 2 cubed next, I would get that 8 back. Property 6 says if you do a logarithm of a product, that you can do log of the first factor plus log of the second factor. Property 7 is if you do log of a quotient, this means you can do log of the numerator minus log of the denominator. Property 8, if you have log base b of a raised to the c, and this time the b and a don't match, unlike up here in property 4 where the b's did match, you can at least take this c and bring it down as a coefficient of the logarithm. This is a good time to mention that you can also do this backwards. If you start with a coefficient of a logarithm, you can take that c and move it up as a power on the argument of the log. In fact, all of these properties can be done backwards. If you subtract 2 logs of the same base, you can combine them into one log by dividing their arguments to make a new argument. If you're adding 2 logs of the same base, you can multiply their arguments to make the argument of a new log of the same base. And property 9 is called the change of base property. If you have a log base b of a, you can write this as a fraction of 2 logs, where the argument of the numerator matches the original argument. The argument of the denominator is what used to be the base of the original log, and then you get to choose these c's, any base you want as long as it's a positive base, not 1. So if you choose those c's to be 10, then you can write log base b of a as common log a over common log b. Or if you choose the base to be e, you can write this as natural log of a over natural log of b, etc. This list would go forever because there are infinitely many choices of c that could be made here. I encourage you on your own time to go through the second 2 columns of this table and how they are simply variations of this first column. Now write each expression below in a new way using at least one property from the list above. Now I'm going to use this numbering system for the properties in my notes to indicate which property I'm using and when. So in this first case, I have log base 2 of 4 to the x. The 2 and the 4 don't match, so that makes me think use property 8, in which case I can take this x and bring it down as a coefficient. So this will be equal to x times log base 2 of 4. And I'll put a little 8 above this equal sign to indicate which property I used. And now I could simplify further by considering, well, what is log base 2 of 4? Well, what power is needed on 2 to produce 4? And that answer, of course, is 2. So we get just times 2. You could, in theory, give property 1 credit for this. And then we have 2x as a final simplification. Now, in this next case, it's tempting to see this square here and do the same thing that we just did and move that square down. However, that square is only a power on the x. It's not a power on the 4. So the first thing I'm going to do here is actually property 6, because I have an argument that's a product of 4 and x squared. Now this is a log without a visible base, so this is log 10. So we can write this as, again, log base 10, or just log, of the first factor plus log of the second factor. And this was using property 6. Now log 4 does not simplify without a calculator, so I won't take that any further. But what I can do now with this 2 is bring it down in front of this second logarithm using property 8. And we'll stop this one here. Now in this next one, we have log of a fraction. So this is a clear case of doing property 7. So I will write this as log of the numerator minus log of the denominator. Now I could take this a little bit further. A square root is the same thing as a 1/2 power on that x. And now I can use property 8 and bring that power down in front of that logarithm. And we'll call this one done. Now all of these so far, you should in theory be able to begin with the result and then step by step working back towards the original by reversing all the steps. Same thing here. If you begin with this, you move that 2 up to make this line, and then use property 6 backwards to reproduce the original. Here you move that 1/2 up as a power to get this line, and then that power can be rewritten as a square root, and then use property 7 backwards to get the original. In fact, this next example gives us a chance to work backwards. I'm going to take this 3 and move it up as a power on the x first. That was using property 8 backwards. And now I have a natural log plus another natural log. And then you have property 6, natural log version of it. If you add 2 natural logs, you can multiply their arguments into a new argument. So this just becomes natural log of, and my new argument is 5x cubed. And the last one, if ever you have a logarithm divided by another logarithm of the same base, then you want to use property 9 backwards. So here's 2 natural logs being divided, can be condensed into a single logarithm. So we write log. The argument 2 from the denominator becomes the base of this new logarithm, and the argument 8 is the argument of this new logarithm. So we get log base 2 of 8. And now ask yourself, what power is needed on 2 to produce 8? Is it a convenient number? The answer is yes, it's a convenient 3. You could give property 1 credit for this thinking. Okay, going on to the next page. A logarithm function has the form f of x equals log base b of x, where b is positive but not 1. Use technology to simultaneously graph both functions below for various choices of the base. Generalize your findings. Okay, we'll graph both f of x equals b to the x and g of x equals log base b of x. All right, so I typed both these functions in, created a slider for b, and then I set the limits of b from 0 to 5 and a step size of 0.1. Drag b to 0, and we don't have anything interesting to look at. Same thing is true when the base is 1. So we will avoid these values. Let me change the base to 2. So when b is 2, the blue graph is the graph of y equals 2 to the x passing through 0, 1, and 1, 2. The red graph is the graph of y equals log base 2 of x passing through 1, 0, and 2, 1. These two graphs are symmetric about the diagonal line y equals x. Now if I change the base to 3, notice the symmetries and the new points. Change the base to 4, notice the symmetries preserved, and look at the coordinates of the points. Base 5, similar. Now we know that the blue graph will be a growing exponential if the base is more than 1. What if the base is less than 1, such as 0.5? So the blue graph is 0.5 raised to the x, which is a decaying exponential, and the red graph is log base 0.5 of x. And there's still a symmetry about the diagonal line y equals x, and notice the coordinates of the points. I'll drag the base to 0, let it vary between 0 and 3, and hit play. If b is less than 1, both functions are decreasing. If b is more than 1, both functions are increasing. The domain of the blue is always all real numbers, and its range is 0 to infinity, and the domain and range of the red are just the reverse. The domain of the red is 0 to infinity, and the range of the red is all real numbers. So for an exponential function, the domain will always be all real numbers, and the range will be positive outputs only. And the function log base b of x is the inverse function of b raised to the x. Its domain is 0 to infinity, meaning this x here must be positive, can't be 0 or negative, and its range is all real numbers. If b is more than 1, then the exponential will be a growing exponential, passing through 0, 1, and a second point will be 1b. But the logarithm graph will pass through 1, 0, and a second point will be b1. It will follow the y-axis as an asymptote and then arch over into the first quadrant. Now if b is between 0 and 1, we'll have a decaying exponential, passing through 0, 1, and a second point will be 1b. The logarithm graph will also be decreasing, going through 1, 0, and b1, and will arch into the fourth quadrant. Now I would like to explore the case when b is Euler's constant e, and we get these two important graphs. The blue one is y equals e to the x, and the red one is log base e of x, which is natural log of x. The blue graph goes through 0, 1, and 1e, and the red graph goes through 1, 0, and e1. So the blue graph is e to the x, the red graph is natural log of x. Now we just made the claim that the range of any of these red functions is all real numbers, suggesting that even though we see portions of these log graphs that flatten out, that all y coordinates are still possible. Let's go back to the base being 2, focus only on log base 2 of x, and let me put a horizontal line in here such as y equals 10, change my vertical scale so we can see it, and in this viewing window it looks like the red graph may never reach the black graph as we go off to the right. But let me change my x scale. And you can notice that if we go far enough to the right, in fact 1024, we finally get to a height of 10. Well, let me increase that height to 20, change my vertical scale so we can see it, and continue to go off to the right. And you can still see that eventually, by the time we get to 1,048,576 for x, we finally get to a height of 20. In fact, no matter how high of a y-coordinate I pick, if we go far enough to the right, the logarithm graph will exceed that height. So the end behaviors, focusing on the logarithm graphs, as x goes right forever in this first case, y does approach infinity. Now the red graph has a restricted domain. I can't let x approach negative infinity, but the furthest left I can go is to let x approach 0 from the right. And as we do that, these y-coordinates drop down to negative infinity. In this middle case, as x approaches infinity, the y-coordinates of the red graph will approach negative infinity. And as x approaches 0 from the right, the y-coordinates will approach positive infinity. So these end behaviors right here would be the same end behaviors for y equals natural log of x. For each function below, graph it on the same grid, identify any asymptotes, give the domain a range, and determine the end behaviors. Let's begin with the graph of y equals 3 to the x. This graph is a growing exponential that passes through 0, 1, and 1, 3. If I had made a table of 2 points, if you let x be 0, 3 to the 0 is 1. If you let x be 1, 3 to the 1 is 3, confirming our points 0, 1, and 1, 3. We'll take the red graph, and one consideration is to first convert it to exponential form. So the base of the log is 3, and that will be raised to the y, and that should be equal to the argument of the log x. We'll make a similar table of points for this, but pick the y-coordinates first. Let y be 0, 3 to the 0 is 1, and that produces x. Let y be 1, 3 to the 1 is 3, and that produces x. This is the reason why we get the same coordinates, just in reverse positions. So 1, 0, and 3, 1 are 2 points on this graph, and we have this logarithm. Now let's focus on the third function. The third function is a transformation of the red function. This negative will reflect the logarithm around the x-axis. Then we're going to shift left 2, and then finally shift down 1. Here's the reflection of the red across the x-axis. Then we're going to shift left 2 units. Notice where the new vertical asymptote is, and then down 1 unit. So my new vertical asymptote will be at x equals negative 2. And 2 points will be 1, negative 2, and negative 1, negative 1. So the domain of the orange graph is going to be x must be more than negative 2, or you can say negative 2 to infinity. The range will be all real numbers. Even though the graph flattens out as we go to the right, the y-coordinates will drop to negative infinity eventually. As x approaches infinity, therefore, y will approach negative infinity, and as x approaches negative 2, but from the right, the y-coordinates will follow that asymptote up and approach positive infinity. Okay, let's go to the next page. For each function below, determine the end behaviors and confirm with technology. For this first case, I'm going to focus on where the x's are. We have an exponential e to the negative x. The graph of y equals e to the x is a growing exponential, and the graph of y equals e to the negative x reflect this around the y-axis, and we get this decaying exponential. Focus on this graph. As x goes to infinity, these y-coordinates shrink to 0. So this portion of our function y approaches 0 as x goes to infinity. But in the other direction, the y-coordinates go up to positive infinity as the x-coordinates go to negative infinity. So now we want to focus on what this overall fraction is doing. So as x increases forever, the y-coordinates of this function, let's call this y sub 1. In the second example, we'll call y sub 2. But y sub 1 will approach 3 over 1 plus 2 times a 0. So we'll approach 3 over 1, or simply 3. And as x approaches negative infinity, y sub 1 will approach 3 over 1 plus 2 infinity. We'll double infinity and add 1 is still infinity. So we have 3 over an ever-growing denominator, which tends to 0. Let's confirm this by graphing y sub 1. Here's a graph of our function. As we go off to the right, the y-coordinates of the blue graph get closer to y equals 3. And as we go off to the left, the y-coordinates of the blue function get closer to a y-coordinate of 0. Now looking at y sub 2, focus on this function here, the arctangent. From previous lessons, we learned that the arctangent graph is a graph that also has 2 different horizontal asymptotes. The lower one is at y equals negative pi halves, and the upper one is at y equals positive pi halves. Now this 2 will produce a horizontal stretch by a factor of 1/2, which will compress the graph horizontally, but it will not change the heights of the asymptotes. So this tells me that this will approach pi halves still as x gets large, but this will approach negative pi halves as x approaches negative infinity. So now I want to study what the overall function y2 will do. So as x goes to positive infinity, y sub 2 will approach 3 minus pi halves. As x approaches negative infinity, y2 will approach 3 minus negative pi halves. So this winds up becoming 3 plus pi halves. Now if you wanted to keep thinking about transformations, this negative in front of the arctangent would be a reflection around the x-axis, and this positive 3 in the front would be a shift up 3. So here's a graph of y equals arctangent of x. It has two horizontal asymptotes, one at pi halves, one at negative pi halves. If I put a 2 in front of the x in our argument, we get the horizontal compression by a factor of 1/2, but that does not change the heights of the asymptotes. If I put a negative in front of this, we do get the reflection around the x-axis, and then if I put a 3 to lead this off, everything here will shift up 3, including the asymptotes. So one asymptote will now be 3 plus pi halves, and the other asymptote will be 3 minus pi halves. As we go right forever, we can clearly see that the blue graph is approaching the lower asymptote, which is 3 minus pi halves. And as we go left forever, the blue graph is approaching the upper asymptote, which is y equals 3 plus pi halves, confirming our analysis here. Okay, and this concludes the second part of our lesson on analyzing functions.